So, hello guys, my name is Rafaela, and in this presentation, we're gonna talk about my work with Professor Sandro in the astrophysics group. We titled Environmental Mapping of Post-Starburst Galaxies, and then we're gonna talk about in more details how Spectra tell the history of stars and galaxies. Nice. So in this presentation, I will show you how, I will try to show you how Spectra, how to read iSpectra. So, what is post-starburst galaxies? To start, are a array class of galaxies. Até acho que dá para desligar uns. Pronto. Array class of galaxies that have truncated starburst suddenly. So, burst is an explosion. It refers to the intensity star formation. So what we have here is a galaxy who have formed stars like crazy, and suddenly it stopped to form stars. And we can see it. How do I know that? How do I know this information? Just looking at this beautiful thing that we call spectrum. So I look at this spectrum and I take all this information. And this type of galaxy is in the process of evolution. And that is interesting to study how the evolution of galaxies work. So this is a post-starburst galaxy, and this is the spectrum from this galaxy. What is a spectrum? It's basically the intensity of the light. So here we have the density, but it's the intensity at this side of the light in the different wavelengths. So here we have the blue color here, and here we have the red color. And okay, so the telescope captured the light of the galaxy, and we have a spectrography that works like a grating, diffraction grating. In this grating, we open this light in the different wavelengths. So it works basically just like a prism makes rainbows, but it's more difficult than it seems like. So here is just so you remember what is spectrum. Yeah? So, we know this picture. We have to remember that light is a form of electromagnetic energy, and this energy is here. So here we have the visible spectrum. Here we have infrared wavelength, ultraviolet, radio waves, gamma rays, and radio waves. Here we increase the frequency, and here we increase the wavelength. In my work, we are working in the visible spectrum here. So, first of all, we need to know that it's important to know that normal stars are in a balance that we call hydrostatic equilibrium between the gravitational force which tries to crush the stars, smash the stars, and the force that due to nuclear fusion in its interior, which tries to make the star expand. So here we have a balance between this force and this force. And this is for normal stars. Não está colapsada, vamos ver. And so, the low mass stars, if we have a low mass star, the gravity will act normally. And so we're gonna have a low temperature because it's low gravity. So we have little fusion. And so this type of star, this kind of star, will last longer. So we're gonna have an old star that it lasts billions of years. And by the other hand, if we have high mass stars, we're gonna have gravity acting a lot. So we're gonna have high temperature and an intense fusion. And so its nuclear fuel, its hydrogen runs out quickly. And so this kind of star will die young. Young star to us here is millions of stars, millions of years. Other thing we have to know is spectral classification, and this is the basics. Here we have a blue star, and this is the surface temperature. A blue star actually is the hottest star we have. And the other hand, we have the red stars, is the coolest stars. It goes against what our common sense. We used to think that red color is hot, but actually in science it's not like that. And so how do I know this? By the Bill's laws, it's an empirical law. So when we have high temperature, we're gonna have a lower wavelength. So here we have wavelength, okay? Lower than wavelength is blue color. And so it's the most, it's the hottest star, more hot star, and it have a peak in the blue color. So, how to read this spectra? This spectrum of a galaxy is basically the sum of the spectra of the stars that make up the galaxy. And so here we can see we have a peak in the blue color here, and here is the purple color. And so I look at the spectrum, and I know that I have young stars, and also because the Balmer absorption lines. Absorption lines in the next slide. Okay. The Balmer series is gonna be evident because of the temperature. It's always because of the temperature that the star has. So the temperature about 9,000 kelvins on the surface and the atmosphere of these young stars. So you can imagine here we have a star, and here is the atmosphere of the star. So when the stars like pass through this cold gas, these atoms here will absorb the photons with this specific energy, and the electron here will jump to higher levels. So these photons, since these photons are absorbed, this energy is not in the spectrum. So here we have a missing line. So we have absorption line. So I know again that we have young stars. And here, this is the Balmer series. So when I go from level 2 to level 3, I have red color. Level 2 to level 6 by quantum mechanics. We will have lots of colors in the quantum mechanics. And we're going to have the purple color, each level. So finally, I finished my presentation. Here we have the relation between the emission line in H alpha, here. If I have emission line in H alpha. And what is the relation between the star forming? So here I have a star forming region. This is the Orion Nebula. So it can be seen with naked eye. You can look at the sky at night and you're gonna see the Orion constellation. And right here is my own picture. You can see is the Orion Nebula. So it's very, very cool. You can see here, you know that this is a star forming region. So, what is the relation between this emission line and the star region? Is analogous of the past slide. So, newly formed young stars are very hot, and this emit high energy. And here, we will gonna have ultraviolet radiation. So this radiation will ionize the surrounding gas, and so it will remove the electrons of the atoms from around here. And so when electron is recaptured by the atoms here, again, this electron goes to level 2, for example, which due to the conservation of light, as an electron came from a higher energy level to a lower one, then a photon is liberated. So we're gonna see this emission line. Here's a fake color, as you know. But se a gente coloca o computador, essas coisas são super falsas, tá? Mas in the spectrum, we can see that emission line right. So is it? And so saying this phrase again, now you can understand what I'm saying, as indicated by the law of contribution of emission lines. Here we don't have emission lines. So I know this spectrum is of a strong galaxy, which is not forming stars. And I know by the Balmer series that we have young stars here. So it's like that. Why are we interested in these galaxies then? We are interested because they are considered transitional objects. So through this transitional object we can infer and discover how the evolution of the galaxy happens. And next presentation, I will present you more details and the methodology of the work, preliminary results. And I thank you all. Thank you for your attention. I hope you have enjoyed it.